All right, here's our last unit of the semester. We're going to do a few sections from chapter 15 and a little bit of chapter 16. Together, those will be combined into our last unit, and we'll take our last test covering those sections. So all semester long, we've been talking about derivatives, right? Instantaneous rate of change, slope of the tangent line, marginal cost, marginal profit, marginal revenue. But what happens if we know the rate at which the cost is changing, but we want to go backwards and figure out the cost? Or we know the velocity, but we want to know what the position is. Or we know the rate at which water is leaking out of a tank, but we actually want to figure out the amount of water that's leaking out of a tank. And so all of these things make it so that we have to kind of use our derivatives but go backwards. Maybe we know what the derivative is and we want to figure out what the original function is. We want to find what's called the antiderivative. Okay, so we're going to introduce a little bit of new notation here. We're going to call big F, capital F, can I call him the original? And then little f is our derivative. So if I give you big F and I ask you to find me the derivative of big F, that's really the same thing as little f. Or what I can say is that big F is the antiderivative of little f. If little f is the derivative and you go backwards, then big F is the antiderivative. Okay? So what if I gave you this little f function? So he is the derivative. The little f derivative is 3x squared. If my derivative was 3x squared, would you be able to figure out what the original function was that has a derivative of 3x squared? Yeah, well, maybe you could use your power rule backwards and recognize that my antiderivative of 3x squared is really x cubed, right? Practice, take the derivative of x cubed. Don't you end up getting 3x squared? And so big F, that x cubed, is what we call the antiderivative of little f. But wait a second, couldn't that big F, that antiderivative, be x cubed plus 7? Because what's the derivative of x cubed plus 7? Isn't it still 3x squared? Because the derivative of 7 is just 0. So my original function could be x cubed plus 7, and I would still get the same derivative. But wait a second, couldn't then my original function be x cubed, I don't know, maybe minus 15? He would still have a derivative of 3x squared. So that means when I go to take an antiderivative, my original function could actually be anything with a constant in the back there. So I could really say that my original function is x cubed plus c, meaning any constant could be in the back and I would still have a derivative of 3x squared. Okay? And so we're going to introduce that notation of finding an antiderivative. Means if I am given a little f, a derivative, then I can find his antiderivative as long as I add a constant of integration. It's what it's called, that plus c at the back. This is also known as an indefinite integral. So another notation is adding this little integration sign. So I could ask you the same question two different ways. I could say, hey guys, I have a derivative. It is 3x squared, and I want you to find the antiderivative. Or I want you to find me big F. Or I can take that same exact question and instead of using all of that words, say, hey guys, find me the integral of little f. Meaning, I want you to find me the antiderivative of little f. What was the original function that has a derivative of little f? Okay, so a couple different notations we're going to start to introduce now when we use antiderivative. And this little dx at the back just means that we're finding the antiderivative with respect to x. Kind of like when we did our implicit differentiation. When we found the derivative with respect to x, remember we added that dy over dx? Well, this is kind of the same notation. It's just saying that we're finding the antiderivative and making sure that those two variables match. Okay? All right, so integration is another word for anti-differentiation. And so I could ask you to find me the integral of 2x with respect to x. And so that means if 2x is the derivative, then what was the original function that it came from? What is his antiderivative? Well, we can maybe use our power rule to recognize that the antiderivative of 2x is really x squared. But remember, it's x squared plus any number, right? So now, as soon as I take that antiderivative, I have to make sure that I add that constant of integration. That's going to be worth points on your test. So the integral of 2x with respect to x is really x squared plus c. Okay? Again, if I asked you to find me the derivative, now we got to train our brain to go back and forth, so be careful. If I ask you to find me the derivative of x to the fifth, I could really say the derivative is 5x to the fourth, right? So that means if I reversed it and said, hey, find me the integral of 5x to the fourth, or the antiderivative, well, what original function has a derivative of 5x to the fourth? Well, isn't that my x to the fifth? But actually, x to the fifth plus c, because any constant could be back there and still have a derivative of 5x to the fourth. So my antiderivative would be x to the fifth plus c. If you've noticed, maybe you've noticed a pattern that I can use when I go to use my power rule backwards. If you've noticed, what I've done is I've actually added 1 to the exponent. Remember, kind of opposite of what we did when we found derivatives. But then we have to make sure that we go back and divide by that new exponent. Let me show you again. If I have the integral of 5x to the fourth, and I'm asking you to find the antiderivative, we're going to add 1 to the exponent, so now it's a 5. And then I'm going to divide by that new exponent, which is that 5. And don't those go away? And that's how I got my x to the fifth. So we have rules, just like we have rules for derivatives, we now have rules for antiderivatives, or integration rules. So anytime I have a integral that is an x to the nth power, just like we have our power rule with derivatives, we have our power rule with antiderivatives, where we add 1 to the exponent and divide by that new exponent, always making sure that we add that constant of integration at the back. Let's practice them. Looking at example number 1, it asks us to use the power rule to find each indefinite integral. Find me the antiderivative of t cubed. What original function has a derivative of t cubed? Integrate it for me. Well, let's use our new power rule, our reverse power rule, to add 1 to our exponent. So now our new exponent is what? 4. And then let's divide by that new exponent. And so I end up getting t to the fourth over 4. But remember, make sure you add that constant of integration, that plus c. So if my original function was t to the fourth over 4 plus c, could we double check and find his derivative to make sure I got that right? Remember, when I find the derivative, I bring that exponent forward. So I have a 1/4 right now. If I bring the 4 forward and I subtract 1 from the exponent, I end up getting this. The derivative of any constant is 0, and then don't those 4's cancel? So that leaves me with a derivative of t cubed, which is what I started with, and so I know I got the correct answer. So the antiderivative of t cubed is really t to the fourth over 4. Okay? Look at b with me. B looks a little bit different. B looks a little bit different because that variable is on the denominator. And right now we don't have a quotient rule for antiderivatives. We only know one rule so far, and that's the power rule. So B is an example of something that we have to kind of rewrite, manipulate a little bit so it looks like the rule that we do know. So how do you think we're going to have to rewrite 1 over t squared so that it looks like the power rule? Yeah, we're going to bring it up to the top. So now I'm integrating t to the negative 2. I'm integrating t to the negative 2 with respect to t. That's just saying that our variables match, and so I don't have to worry about any sort of implicit anti-differentiation. And so if I'm going to use my power rule for antiderivatives, remember, power rule for antiderivatives now means we're going to add 1 to the exponent and divide by that new exponent. So if I add 1 to the exponent, what's negative 2 plus 1? And then I have to make sure that I divide by that new exponent. So what is that? Negative 1, and then I'm going to divide by another negative 1. And then don't forget, you add your constant of integration at the back, always, always, always. I'm going to go ahead and make that negative exponent positive. I don't like this t to the negative 1, so I'm going to drop it down to the bottom. And so I end up having a negative 1 over t to the first, or just t, plus c. And I just move that negative out in front. It means the same thing as putting it at the bottom or putting it at the top, as long as you don't put it on both. Okay? All right, look at c. Oh, there's my beautiful red flag again. As soon as we see that square root, what do we think about? Yeah, we think about making it into a 1/2. And so now the problem says I want you to integrate x to the 1/2 with respect to x. I want you to find me the antiderivative of x to the 1/2. So using my power rule, just like I did in the last couple examples, let's add 1 to the exponent. Now you need a common denominator. So can I say 2 over 2? So my new exponent is what, 3/2? And then I'm going to go through and I'm going to divide by 3/2. But when I divide by 3/2, doesn't that look weird? If I have x to the 3/2 divided by 3/2, isn't that a triple layer fraction? So instead of dividing by 3/2, isn't that the same thing as multiplying by the reciprocal? So instead of dividing by 3/2, can I multiply by 2/3? That means then I have the 2x to the 3/2 on top, and I have the 3 on my denominator. That's where I got the 2x to the 3/2 over 3. Remember, plus c is my constant of integration. You can always double check by finding the derivative, and that should be back to where you started, the x to the 1/2. All right, look at D. Look at D really carefully. It's asking us to integrate. But integrate what? There's nothing there. Well, be careful. What's really there if there's nothing there? Isn't that an invisible 1? And so be careful now. What do you think the antiderivative of 1 is? What original equation would have a derivative of 1? Did you say x? X plus c though, right? Don't forget your constant of integration. So the integral of 1 dx is really x plus c. The antiderivative of 1 is really x plus c. Okay? Make sure that you practice your power rule. We're going to do some more problems. We're going to get a little funner, like I say, as we go along. So make sure that you practice the basic ones before they get